it's a pleasure to be communicating with you. I think this is probably the most long distance lecture that I've given, and I'm delighted to be providing a lecture to the Iraqi Medical Physics Society. Thank you for inviting me, and a special thanks to Aladdin, who was in Canada, and he arranged this communication with the Iraqi Medical Physics Society. Thank you. So I'm going to talk about dose algorithms, in particular dose algorithms for X-rays. Can everyone see the slides?
Not yet.
You don't see the slides yet?
Not yet.
Okay, let me try now.
Yeah,
How's that?
It's coming. It's coming.
Okay.
Yeah. Okay.
Good.
Go on.
So let's go ahead. There's a lot of material, and I don't know if where you are you have a seat belt. Maybe you want to put your seat belt on. Okay, before we begin, I have a serious item. I want to dedicate this lecture to Dr. Jack Cunningham, this individual on the left, and some of you might know him from the famous book, The Physics of Radiology, and he passed away not too long ago. And he was a mentor for me. I learned a lot from Dr. Cunningham. But at the same time, I had a graduate student, Michael Sharp, who became quite an expert on the Pinnacle treatment planning system software. And unfortunately, he succumbed to cancer also not that long ago. So I miss both of these individuals, and I dedicate this lecture to them. So I'm sure you know that dose algorithms are used for a number of procedures. And the one that it's most often used for is the interactive treatment planning and dose optimization. But there is more interest now in also dose reconstruction for the dose of the day, the dose distribution of the day. And this can use machine log files or an electronic portal imaging device with back projection. And then a dose reoptimization is also sometimes done. And these can then be combined on a per fraction basis into the accumulated dose that would be the best prediction of the patient's actual dose distribution inside their tissue. So there's a lot of activity that requires accurate dose algorithms. So a bit of motivation for the lecture. Why are we discussing this? Well, one, dose distributions are a critical element of treatment planning. And if there are systematic errors in the dose prediction, remember that they will persist throughout the treatment course from beginning to end. Secondly, there have been major gains in computer performance with GPUs and CPUs, and that allows fewer assumptions to be made, but we've got to make sure those assumptions are okay. There's a lot of techniques that are evolving, IMRT, VMAT, image-guided adaptive radiotherapy, and futuristically, again, the biologically adaptive radiotherapy. So we have to bear in mind that the algorithms that were developed 10 years ago may not be able to cover all of these topics. And finally, this is the one I really want to ensure everybody realizes, that especially those of you who are still in training in Iraq, clinical software cannot be treated as a black box. You can't just run the computer system and assume that the correct answer will come out. And a reminder that the US FDA approval process does not test dose accuracy. They are more concerned about the quality assurance of the software process. They are not responsible to give a statement on dose accuracy. So here's the outline for today. I wrote it here in French, topics du jour of the day, because in Canada we are bilingual, some of us anyway. And I want to start with the evolutionary pressures that move algorithms forward. This is a slide from my graduate student, Rock Mackey, and it shows that in the 1950s era, most of the developments were on radiation physics and radiation machines. There were betatrons that had been developed earlier on. There was radiation using radium sources, and eventually cobalt sources I want to talk about. The second major wave is computer science and technology, which, as you know, has changed our lives in so many ways, including three-dimensional medical imaging. And if we look ahead, it looks like biotechnology with very targeted cellular approaches is what will be coming around the corner. If we look at extrapolation of the computer world, it looks like artificial intelligence and machine learning are really taking off. If you look at the publications in this field, it's just, it's caught fire. It's very active right now. I want to talk a bit about the history of megavoltage machines, in particular, some of the developments and early developments that were made in Canada, because we had an NRX reactor with enormous neutron flux. So we were able to activate cobalt 59 to cobalt 60 in reasonable time. So the Canadian government issued a stamp. This is the one here. And here you see Dr. Harold Johns. He is our hero in Canada. And he is with his first cobalt machine that he built locally in Saskatoon, Saskatchewan. If you can pronounce that, we will make you honorary Canadian members. But he developed these machines in Western Canada. However, the commercial machine, this machine here, called the Eldorado A, was implemented in London, Ontario, right here. And the first patient to be treated, first cancer patient to be treated, that happened in October 1951. In a sense, this was the birth of megavoltage, because before that time, the machines, betatrons, or use of radium was really quite limited and unstable. But cobalt provided a stable megavoltage source. So you can see here the number of cobalt machines in thousands that developed after 1950, the blue line. And then soon that was surpassed by the linear accelerators that have more energy capability and also electron capability. So cobalt somewhat become obsolete, but is still very useful on a world scale. I want to show you this graph. It's a little bit intimidating, but this is a plot of the million instructions per second on a computer per $1,000 invested, per $1,000 US dollars. So this is millions of instructions per second, or MIPS. And you can see that over time, this has really escalated. Here's an Apple IIe computer some of you may have had along the way. Here's some VAX computers. And this was a really active period for the development of algorithms. And we're now at the point we're approaching 10 to the 9th MIPS, or another way to put it, PIPS, which is a peta instruction per second per $1,000. It's remarkable computer power. And also remember that memory has become extremely cheap. This is 256 gigabytes of memory on the size of a guitar pick. I play the guitar, so I had to use something that had to do with that instrument. And you can put 128,000 pictures or audio files on this small space. So the reduced cost of memory, the increasing power has fueled the development of algorithms. So I wanted to show the history in photographs. So here I am, I was mimicking what was done in the 1960s, which was isodose charts on a transparency, where you could put the beams from different directions, and then using a simple calculator, you could add the distributions together and form a dose distribution for the composite number of beams. And this is Jake Van Dyke. I believe he lectured to you last week or the week before. He's my colleague, and in the 1970s, treatment planning was done in Ontario, Canada, using a time-sharing IBM computer. And the isodose was printed out with letters, X's and Y's and P's and Q's. Soon after that, the Artronix PC-12 computer was developed, and this was a standalone computer for treatment planning. It was really the beginning of the personal computers for treatment planning. The big developments occurred as well when Alan Cormack and Gordon Hounsfield, Cormack the physicist and Hounsfield the engineer, led to the development of the first brain scanner. And this really changed the calculation methods, because now we had a technique using CT numbers, a way to convert to electron densities relative to water for any kind of tissue in the body. And that was a major advance. Before that, outlines of lungs could be made, but nobody knew their densities in vivo. So this was a big push forward. And here's Jake again many years later on a Theraplan system with, you can see the CT images here. So here's another summary of all these advances. 1960s, most of the dosimetry was done in a water tank. There's still a lot of that being done, but that was almost the only dosimetry. In time, around the 1970s, then models were developed to manage the photon scattering in an all-water patient. Going a bit more forward, then the patient was pixelated with CT images, and in addition, photon scattering was also taken into account point by point. Next, electron transport was added to the algorithms. So here we have photons, but if you look at the electrons, especially in lung, they can travel quite a distance, and we cannot assume that the electrons are deposited on the spot. So these red lines here will appear throughout my lecture, and they designate electrons. And you'll see later that I am in love with electrons, and they are the ones that deposit dose. Looking ahead, if you have multiple instances of the patient per fraction, then you can do the calculations on each of the images and then warp the images to bring them back to a common coordinate system and add up the doses to predict the dose distribution received by the patient after n fractions. Adding human radiobiology has been a promise for 50 years, and it's still not quite refined enough, but that's coming. And I wanted to talk about a little bit artificial intelligence because I'm not sure where that is going, but it's certainly a very active field right now. So I want to talk about accuracy and dosimetry, and in particular, when we see these dose distributions on the screen, do we get what we have on the screen? Does that happen in the tissue? So this is another way to look at it. One radiation oncologist once told me that his job was to hit the tumor and miss the patient. I think that's a good summary of treatment planning. And also in the Hippocratic Oath, when medical doctors are graduated, they also make a commitment to do no harm. So that's precisely what we try to do. Here we try to target a lung lesion, but not affect the lung as much and avoid the other side, the other lung. This is a plot of the probability of normal tissue complications on this side and tumor control on this side. A lot of graphs like this are incorrect in the textbooks. Sometimes they flip it around, they put the tumor on the other side. I prefer to do it this way, that the normal tissues are more sensitive than the target. And if that's the case, you cannot use a single dose of radiation. You must apply a dose gradient. Give a high dose to the target and a lower dose to the normal tissues, and that has been the whole goal of IMRT. I want to talk a bit about uncertainties and accuracy. If you are, for example, at the high end of tissue complication, then swinging back and forth can affect the efficacy of the treatment. So if we have sloppy setups, for example, and here, if we have at the bottom end also some variations in the setup, they can make the complications rise to a higher level. And I also want to mention that we sometimes think that if everything averages out, we don't need to worry about this. But the fact is that biologically, things do not average out because these curves are not linear. It's a non-linear system. So the IAEA has come up with a principle that doses should be calculated as accurately as is reasonably achievable. And by dose, they mean the delivered dose, which includes the dose calculation as a step. They found by looking at a large number of target sites and prescriptions that vary the dose, the volume, or the time of delivery, that there's no single number that we can put. We can't say doses have to be computed to within 2%, because sometimes more uncertainty would not matter. and sometimes it would matter. So that's why they came up with this principle, which is almost the same as the radiation protection principle, to do our best to get doses down as low as accurately as possible. And again, I mentioned earlier that clinical software cannot be treated as a black box. So local quality assurance and vigilance is important, especially since there are software upgrades and there are new treatment techniques. An algorithm that worked for one treatment technique may not be so suitable for another one. An example might be stereotactic small beams. And 3D dosimetry has also evolved, so it's possible to do things in 3D and also include what some people call end-to-end quality assurance. So have a phantom, perhaps a gel, that is treated with many fractions and then look at the final dose distributions end to end. So let's look at the toolbox. Now this is a bit of a review, and for you that are already practicing medical physics, I might be boring you with this section, but I understood that there were some trainees also in your meeting tonight, so that's why I included this. So if we look at the building blocks, the real building blocks are the interaction cross sections, Compton interactions, photoelectric effect, etc., etc. And then building on that, the Monte Carlo and Boltzmann methods rely on these cross sections. And finally, an approximation to these methods is the convolution superposition method. So these are all built together. Now I'm going to flash a lot of pictures, and I don't think you need to recognize everyone, but the fundamentalists, obviously Einstein, every time we treat a patient, the electrons that are knocked on by the photons are traveling at relativistic speed. So Albert's been involved, Röntgen obviously with the early X-rays, Marie Curie, the daughter Irene Curie, Arthur Compton, Hans Bethe, and here's Boltzmann, Ludwig Boltzmann. We'll talk about him later. Now, the implementation of Monte Carlo and Boltzmann methods came about because of these individuals. I'll only flag a few of them. This is Martin Berger, who did a lot of great work on Monte Carlo methods. This is Ralph Nelson at the SLAC accelerator in the US, California. This is Dave Rogers and Alex Bialayev. These two are Canadian guys who developed the EGS code. And this is Pedro Andreu. And these two individuals are the ones that have developed the Boltzmann codes. This is Jim Duderstadt and Todd Waring of the Varian Company. On the convolution side, these are the innovators, and I'm especially proud of Rock Mackey, who was a former graduate student who started this ball rolling, and great contributions from Anders Anaho, Roddy Mohan, and Art Boyer along the way. So that's these are the people that produced what I'm going to be talking about. I don't take credit for everything that I will present today. These are the people that laid it all down. Now, let's start with the cross sections. These are probability maps as a function of atomic number and energy. I want to focus on the Compton one especially. So you can see that for most tissues, let's say with tissues, atomic numbers less than 10, that the probability of a Compton interaction is very high. Everything here is reddish color. 90 to 100% of the interactions in the body will be by the Compton method. Photoelectric events happen at lower energy. They certainly can happen within the head of the machine, but in the patient, Compton is what matters. Same with triplet and pair production. That can happen in the head of the machine, but is quite rare in the patient, except maybe if they have some metallic implants. Anyway, if you are a student of the radiation physics, don't forget the Compton effect. If you forget the other two, you're partly forgiven. Let's have a look at a photon history. Here's a photon, 10 MeV. It will interact in a voxel, and the terma is the total energy released per unit mass. So 10 MeV would be the terma, because that's the amount of energy that was released to a scattered photon and to the electron in blue here. The kerma is the part that was released to the blue electron. Now I made this up, 7.3 MeV. And then this electron travels through tissue, and then at a certain voxel, we calculate the amount of energy deposited along the red line. That's what the dose is. The collision kerma is the amount of such energy that is available for this kind of interaction. So we remove from the blue line, we remove bremsstrahlung, which is here. Now the bremsstrahlung could again release an electron down here, and we could score that. And the same can happen with the scattered photon here. These distant long-range particles are sometimes called the skerma. That's not in the textbook, and that's the scattered energy released per unit mass. So there's a lot of IRMA quantities, and we don't need to worry about them too much, but you have them here for your reference if you want to look at these later. I will be providing the slides to the organizers, and they will send you a PDF file later of all these slides. Now, I can't be from Canada and not talk about hockey. So I want to point out that while these players carry energy and carry the puck, this little black thing, everywhere on the ice, what really matters is to put the puck into the net. And essentially, that happens because of the electrons. The photons can go all over the place in the patient. What matters is the electrons and how they interact within a voxel. So, just to remind you of the dose buildup curves, if we look at the spread of electron energy, it looks something like this. This is called the kernel. And if we have a beam coming from the left, the photon kerma, the collision kerma, would be this purple line here. But at each location, we have the release of electron energy, and I just made a rough sketch of what that might look like. So that's the electron pattern downstream. And then every point on here releases one, sometimes at less intensity because of photon attenuation, and another, all the way down. And that's how the buildup curve is created, by the overlap of electrons coming from upstream and the ones that are released within a voxel here. And I like to take all these points and put them in the bucket. That's the dose bucket. That's what the dose is. And I'm sure you've seen these depth dose curves. So we have here the kerma curve, which is this one. And then we have the dose equals the kerma, one point, this magical point where we have charged particle equilibrium. But the message I have is that this is a very rare point, even in a depth dose curve. More often, we have disequilibrium. There is no equilibrium, and the dose is much less than the collision kerma here, because we have electrons that can come into a region and also leave the region. So this is important. And then here, even in a water situation, if you have very small field sizes, like in stereotactic radiosurgery, you can have disequilibrium. The buildup doesn't go all the way up. It can be below the maximum amount. And the dose, again, would not be the same as the collision kerma, but it would be proportional to it. There'd be a ratio between them, these two curves. So I'm just putting this out to give, again, the importance of electrons. And this is, again, Dr. Harold Johns, who's the Canadian hero of medical physics. And he described this beautifully in his book, the whole idea of keeping your eye on the electrons. So what can cause disequilibrium? Because if there is disequilibrium, we have a deficit of dose, a sudden drop in the dose. What can cause this disequilibrium? Well, we talked about buildup regions, but the penumbra of a beam is also a region of disequilibrium. Like when we see field size and we see the penumbra, sometimes we think that penumbra is due to the size of the focal spot, say in a linear accelerator, but most of that penumbra is due to the electrons that are coming to the edge of the beam, coming out, and there's no electrons from outside the beam coming in to replenish the supply. So radiosurgery beams we've talked about, even IMRT, if there are small beamlets, we can have disequilibrium. The biggest effect is from inhomogeneous tissue. With density and atomic variations, there's interface effects, there's electrons that can build up or build down, and these can affect equilibrium. A little less common, although with MRI Linacs, this is something to be considered. There can be electric and magnetic fields that can also affect equilibrium because the electrons will be going in a circular path and their range might be shortened. Here's an example of these electrons in a situation with water and then low density and then water again. So this is a slab lung phantom, and you can see for small fields here, there are electrons generated here in green, and they go into the tissue here with elongated range, but there aren't very many electrons that come back to replenish the ones that went out. These red ones are generated in the lung, and the purple ones are generated at the back end in water again. If you expand the field size, then you can start to see some equilibrium here if you use your imagination, because there are electrons that fly out, but because there's enough electrons coming from the outside region, the lateral region, it builds up again, and we have a reasonable dose. Here the electron doses, and you can see the buildup curve here in water, then a depression as electrons leave, but then there's a buildup of the lung electrons, and so we get a drop in the dose, not an increase, which you might expect intuitively. But if you have enough of a field size, you do get what is more reasonably, some persistence of the photon fluence, and that's fine. But no equilibrium is dangerous. So let's just see what that looks like in 3D. So we have doses here going across this phantom again, the same one as before, and you can see the depth doses go up, and then at 6 MeV, which is equivalent to an 18 MV X-ray beam, you can see that the dose is not increased in lung, but takes a nosedive because of this equilibrium. And if the energy is lower, this is not as serious a problem because the range of the electrons is so much shorter. This is a 3 rendering of the situation that was done by Michael Sharp, actually. This is the danger zone where you can end up with low doses when you least expect it. So many roads lead to dose. So dose, the reminder, is just the energy per unit mass in a voxel. And again, I'm emphasizing it's these tracks, the red ones, that deposit the dose within the voxel. The photons are just energy carriers, not energy depositors. So a good way to think about the voxel is think of a customs officer and look at all the borders in which, imagine this is a country, all the borders and looking at the energy that comes in or out of a border. If we have this equation for charged particles using the stopping power and the fluence of the particles, you can calculate the dose within the voxel in this manner using stopping powers. The equivalent of that would be if you want to check how much money was deposited in a country, you could probably monitor the credit cards of the individuals that come into the country and see how much they spent while they were in the country. So that's this equation. But there's other ways to get a dose. For example, you can monitor all the particles that come into the country, whether they are uncharged photons or charged electrons. And this would give you the energy deposited within. So you look at everything coming out, and then whenever people leave the country, you also ask them, what money do you have in your pocket now, and so on. This sum of the Q is interesting. That one is for internal conversions, like pair production or whatever. And you can think of that as, again, on the money side, this would be electronic transfers of money or out, in or out. So that would take that into account. If we have charged particle equilibrium, the energy carried by electrons coming in and going out is equal. So this term goes to 0, and you get the dose is equal to the Kerma. But that's a rarely used equation because you rarely can guarantee that there is equilibrium. Now I want to introduce something called the divergence theorem. If you want to look at all the particles coming in and all the particles coming out, there is a wonderful divergence theorem that allows you to do that using vector fluence, and we'll describe that a bit later. So these two equations are the same. This uses vector fluence, and this just uses scalar fluences. Monte Carlo and Boltzmann methods use this kind of equation. They look at electrons and they follow them through the path through a pixel. The collapsed cone convolution we'll talk about later actually uses this divergence theorem to look at how the fluences are traveling through the patient. So all the algorithms want to compute the dose accurately, ideally in minutes or even less. And they all solve the same problem using one of those previous equations, but they might differ in their starting physics database. Some might ignore some of the cross sections. For example, if photoelectric events are rare, most of the methods would ignore that. The commissioning of these algorithms is different. They want different types of input data. The assumptions are different and the numerical techniques are different. So they might give different answers because of that. And the main objective is to compromise between accuracy and speed. So here are the algorithms that were developed over 50 years. The first are first generations methods, a ratio of tissue air ratios, Batho method, both of which, by the way, are Canadian inventions, equivalent TAR also. And then second generations started to take the electrons into account. So now there was consideration of disequilibrium conditions and some consideration of electron density, but not much consideration of atomic number. The methods I'm going to describe are in this category. They are third generation or late second generation, and they do most of this physics quite well. And the Boltzmann method also does very well, although it ignores radiative transfers, that it ignores Bremsstrahlung and oh, I forget the other one. But so let's start. Believe it or not, this was just the introduction. Let's start the lecture now. We're looking under the hood to see how the treatment planning system is working. Let's do convolution first. Convolution is a very simple idea. If we isolate one voxel in the patient and we look at photons that interacted only in that voxel, those photons will liberate electrons and scattered photons, including these charged particles, and form a pattern. I kind of think of this as a perfume bottle with the primary photon impulse here and the scattered particles here, scattered radiation. And they can be electrons and or photons. And these kernels have been computed by Monte Carlo methods. And here's what they look like. It's quite fascinating. So on the left here, this is the primary kernel. This is the pattern for only the electrons. They don't go very far. So it's a blob here. If you allow the photons to scatter once and then look at where the electrons deposit those, that's what that looks like. Second scatter is a little less prevalent. It's darker. And they also travel quite diffusely. Multiple scatter is very diffuse and not terribly bright. Bremsstrahlung and annihilation are the radiative particles that I talked about earlier, and they can be quite bright because they're generated from here, for example. The Bremsstrahlung produces these. And then the total is the sum of all of these. The hot spot is the electrons near the interaction point, and the rest are scattered radiations more further away. These were first published, and they were called dose spread arrays, and they were lookup tables, and they're available. And then later, Anders Anaho, he did curve fit expressions that represent this very well, and the expressions are really nice. They're just basically two exponentials, and they describe the hot spot here and then a long tail for the photons. So this is quite useful when you're doing calculations. The convolution is a two-step operation. First, you have the impulse. That would be at this location, the liberation of energy, and then the spread of that energy with the kernels. The first step is easy to do. You just do a line trace through the patient, going through all the pixels, and do an exponential attenuation. It's trivial. The next one's a bit more complicated. If it's in all water medium, it's easy. But if not, then we have a problem with inhomogeneity. So let's look at all water. The dose everywhere is basically the terma I talked about earlier, total energy released per unit mass at the source, that's at a interaction point, and then spreading the dose through the kernel K at every location using only the difference of their locations. So that means that that kernel has the same shape everywhere. Its shape is not changed, but we change its intensity because of the photon attenuation. So you have a sharp terma beam, and when you convolve it with these patterns, you end up blurring that deposition pattern, and you have a blurred dose distribution, which is very nice. It has the build-up region in it, and it has the penumbra flaring here. So that's kind of nice. And if this is for the students and the trainees, just think of convolution as a blurring process. You take Albert here, and you take this blurred operator, and you put it at every point on his hair and on his face and so on, you end up with a blurred distribution or a blurred Einstein because of this scattered in energy. So what happens if you're in inhomogeneous tissue? Well, that's down here. You have to do some ray tracing between the source and the destination. It's a radiological path adjustment. It's not too difficult. But there's other second order effects you need to worry about as well. A divergent beam, especially large field sizes, you have to tilt the kernel. Basically make it align with the ray. And if you have a polyenergetic beam, which you always do for the LINAC, for example, then you have to know the spectrum of the photons and weight the kernels to give you an effective kernel. So these are relatively smaller effects compared to inhomogeneities. So here's an example of an inhomogeneity. The lung is here, and you can see the kernel in water is fairly well behaved, but if you start to take into account the inhomogeneity, you can see the kernel gets distorted. And you have to do this at every point in the patient. So this is very time consuming. So a recap, superposition compared to convolution. Convolution uses a fixed kernel shape, and superposition uses a kernel that varies point to point. If you're an imaging physicist, you will know that this is sometimes called a spatially invariant kernel, and this is a spatially variable kernel when it comes to imaging blurring. The terma is shown here, it's just exponentially attenuated, and the kernel is an effective kernel that takes into account the spectrum of the radiation. And that's what the results look like. In water, you get a very nice dose distribution. In lung, again, we have the bulging of the penumbra because electrons are flying out to the side, and that causes a wider penumbra, and you get a hole in the dose distribution in the middle. So there has been a quest to accelerate convolution calculations, and the best known is the collapsed cone convolution, where the kernel, as shown here, is split into a bunch of mini cones all around. And these cones basically are then collapsed so that you don't follow the minutia of following all the scattered radiation exactly to every other point. You kind of say, well, it's all traveling along one line at each of these collapsed cones. That looks something like this. So this is Anders Enho, who came up with this brilliant idea, actually. And that's me at a younger age. And you can see the kernels are here. They're split into a bunch of small cones along these black lines. And then those cones are collapsed onto like a central axis for each of these. And the energy is propagated along these rays. And that's much easier than going to every point in the neighborhood. And I think by now you probably need a bit of relaxation. So this is from Notre Dame Cathedral in Paris, France. And it just reminds me of the way that these cones are separating in the collapsed cone method, as opposed to having every little point um, talking to the intersection point. You can just split the energy dispersal into these major directions. Once you do the splitting, you then take the energy of these and you collapse it onto a smaller region. That's the collapsed cone. And once you do that, you can propagate all along this red line. It's very efficient. If you're having trouble with this concept, think of this as an umbrella, and you take all the energy from the outside and you fold it in along the axis here. And then you only have to worry about energy propagation along that direction. If you have another analogy you want to cover, the transport lines, those lines, the red lines that I showed earlier, you can think of them as a subway line. And when we have a public transportation system, we don't pick up individual customers at their home. We ask them to come to a station, and they can come in or out along those stations. And that's what the collapsed cone method does. It follows the amount of radiant energy within a voxel, and customers can get on the train, or they can leave the train. When they leave the train, it deposits dose along this line. And this goes on to the next station. Again, new passengers picked up and some disembark, and you deposit the dose along there. And it turns out that this is very efficient. I won't bore you with this. This is just for your reference. The number of calculations for a full superposition method is on the order of n to the 7th, where n is the number of dose voxels. But if you do the collapsed cone convolution, you reduce it to n cubed. That's a big gain. And m is the number of cones used per interaction point. So that's quite a savings. And it works very well. Here's a very complicated case. This is a low density object. This is all water except for that. It's like a lung. And if you go across and take a profile, the old methods that do not take electrons into account would predict that if you're in the shadow of that block, or even a partial shadow, that the dose would go up. Intuitively, that's what you would expect. The fluence of the photons is higher. You just expect an increase in dose, and that is incorrect. The real result is this lower dose here in this lung because of electron disequilibrium, and the collapsed cone method does account for that quite nicely with this very difficult test phantoms. If you ever want to check your computer system, this is a tough one to pass. Okay, let's go to Monte Carlo methods. I think I'll be able to be done in about 20 minutes. So it's named after the famous casino in Monaco, and has to do with gambling and the randomness of the radiation events. And the Monte Carlo method's been used to simulate linear accelerator heads, to generate the energy deposition kernels that we talked about for convolution. It can also be used as an online tool to verify a treatment plan that is suspicious. So if the treatment plan looks a little bit odd, you may have access to a Monte Carlo code which will run the same case in much more detail. It would take longer, but verify your approximate calculation method. Or it can be used offline for commissioning a beam, for example, by calculating all the particles that come down the LINAC head. So let's look at what a Monte Carlo method is. It follows every particle generated by a photon. That includes the electrons, the secondary electrons, Bremsstrahlung, annihilation photons, scattered photons, and positrons. So that's quite comprehensive. There's a lot of physics in these Monte Carlo codes. The disadvantage is it takes a long time to run, and you get a result that has inherent statistical variation. The results are a bit noisy, but if you run 1 billion histories, that noise is quite low. So typically you have to run between 10 to the 6th, 10 to the 9th histories. You can score the fluences, the dose, and all sorts of other things. And the solution evolves gradually as the number of histories goes up. You can tag particles, which is very nice. If you see particles that you're not sure where they're coming from, you can tag them and then look and see where the electrons are coming from, for example. It's very intuitive. I've written some Monte Carlo codes, and it's almost a toy. It's a toy algorithm where you can change so many things and also show the results on a screen and show these particles flying around randomly. This is an analogy if you have trouble with this method. Basically, you launch particles, they interact and scatter throughout the patient, and then you score the result. That could be the dose, for example. I won't bore you with this flow chart here. I put it there just for your reference. If you want to generate a history, you have to select a free path to the next interaction site. Then you have to select what interaction took place. Was it Compton? Was it photoelectric? Was it pair production, for example? And then you have to keep track of the status of all the particles. So let's do a simulation. This is the same probability map I showed earlier. And let's assume that we're in soft tissue, so the atomic number is 10 or less. And we have a photon of 7.5 MeV. So we're here. So we call a random number between 0 and 1. If it lands above this probability, which is 72%, we say it's a pair production event. If it falls below, we say it's a Compton event. And you can clearly see that the Compton events will be more prevalent. So that's pretty straightforward. Now looking at the photons and how we decide if it is a Compton event, where the photons go. This is a scattering angle distribution. Let's just look at the cobalt one here. So the way you do this, and by the way, this may look a little bit different from what you see in the textbook because it's the probability per unit planar angle, not per unit solid angle. So it's a little bit different. But you call one random number here. So basically that interrogates, it says, did the photon scatter at 130 degrees? You call a second random number. If it lands here, you say, yes, it did, and you move on. If you reach a second number here and it comes outside this area, then you say, no, that didn't happen, and you try again. So this is how you can decide randomly how to populate these distributions of scattered photon angles. Electrons in Monte Carlo land are really problematic, and for every algorithm they are, because there's so many interactions that can take place. If you were to simulate every single one, it would take far too long. And Martin Berger came up with this idea of a condensed electron history. And the way it works is it allows and collects some of these scattering events into a bunch. And they use multiple scattering theory to calculate this approximate path. This is called the continuous slowing down approximation. And once in a while, you're allowed to produce a catastrophic large event like Bremsstrahlung here. This saves an enormous amount of time. This is the detailed flowchart just for your reference later if you want to read about it. But the electrons are the time consumers. There are many Monte Carlo codes. They're all listed here again for your reference. EGG's code is very popular, but it's mainly for modeling the LINAC head, not so much for modeling the patient. But there are others that are much more oriented to applications in treatment planning, and some of those are listed here. And finally, I just want to remind you that the accuracy of the Monte Carlo code depends on a number of things. You really have to compute for longer times, and that increases with bigger field sizes, larger patients, and if you want more resolution on your dose calculation, and if you have slow computer hardware. And here are some results, though. I say it takes a long time, but this result was obtained in 10 seconds with 1% noise in the dose. And you can see a distribution for head and neck case here. It's really remarkable that this could be done in 10 seconds. Some of the calculations that were done when we produced the kernels, we used 2 VAX computers across Canada, and they took up 1/2 CPU year to generate just those kernels. And now we can do this in 10 seconds. It's amazing. Here's an interesting application where we had the idea, and nobody has done this clinically, so bear with me. We came up with the idea was, why don't we create a virtual lung shield just by causing disequilibrium, forced disequilibrium. So this is a field size of 6 MV, 3 by 3 centimeters squared, hitting this target. Kind of a radiosurgery treatment, but not quite. If we shrink the field in this direction to 1 centimeter, we will cause a lot of disequilibrium. When we do that, it turns out that the target will get, by comparison with the surrounding tissue, a boost in its dose. And the second advantage of this I call self-motion tracking. If the target moves, the dose will chase it. The dose will automatically re-equilibrate in the target and not in the soft tissues around it. So that's kind of a neat idea that somebody should pick up and run with. I think there is a cancer center in Canada that is trying this out. And it's quite fascinating because you don't need gating. The dose will chase the tumor. Okay, now we get to Boltzmann. This is Ludwig Boltzmann at his computer. Of course, it's an artificial picture. And now we got to think about Boltzmann. And it's important when you think about this Boltzmann method, which is the least known, to think about the flow of particles, much like this here. And also to learn radiometric quantities. I will not have time to describe each of these, but I want to bring emphasis to the flow of radiation, just like a fluid dynamics. And there are vector quantities, currents they're called, and they have a little arrow on top, and those are vectors. We are more familiar down here with scalar quantities of fluence and energy fluence. But if you want to do Boltzmann work, you need to know what these vector quantities are. So let me explain what they are. So at a moment in time, the particle is at this location, R, that's 3 coordinates, and it will be traveling in a certain direction. So for example, in this red direction, and we characterize that by 2 angles, the polar angle, the azimuthal angle. So that's what that is. And we can also monitor by using a perpendicular to the surface element whether the particle is leaving a structure or coming into the structure, because this process of, you can do a dot product, and the cos of this angle will determine if the particle is going out or coming in. So that's very useful. But the important thing is that you now have grouped your particles in what is called a phase space. And the phase space has 3 coordinates for the position, 2 coordinates for the angular direction, and we also track the energy of the particles here. And if this is known everywhere, then theoretically you can compute a dose distribution. Let me do a simple example. Imagine we had a pixel here, or voxel, and we had 1 MeV photons coming in this way and 0.5 MeV coming this way. So the 1 MeV particle is here at the beginning, but if we allow a lot of particles to come in, Compton events will distribute that particle and we'll have a whole spectrum of energies, that one. Same with the half MeV one. It starts here, but over time, if a lot of events take place, it will generate a whole spectrum. And this is just an example of a phase space plot. It's more complicated if you do photons from X-rays because of the electrons that are set in motion. So you actually need 2 of these phase spaces, a photon phase space and an electron phase space, and the particles can exchange back and forth and populate each of these depending on if a photon produces an electron or vice versa, like Bremsstrahlung. So these 2 are constantly updating these fluence counts here based on the interactions. And some of you may have seen phase spaces with accelerators. They're sometimes provided by the manufacturer, and that's just a phase space in a plane. For example, before these collimators or after these collimators, before the patient. and these are available, and there's even some attempts to calculate the phase space after the patient. So you know which particles are there, which ones are going what direction, what energy they have. So I wanted to mention this divergence theorem. I mentioned it earlier. This divergence theorem allows you to monitor the net outflow of particles through a structure. And this is done by taking, as I mentioned earlier, a dot product of the current, which is this J, with the normal to the surface. And this cos angle here is going to flip signs if you're going out of the soccer ball or coming into the soccer ball. So if you do this integral over the whole surface, you end up with this divergence equation that is very useful for calculating the net outflow. And if you remember that if we were doing doses, in and out flows determine the dose. So it's possible to set up a mass energy conservation equation and look at the net outflow, and you get a dose. And you can use divergence theorem, which is much simpler than this mess, to calculate that. So let's do a simple Boltzmann calculation. The net number of particles coming from a volume would be the number of particles that are produced inside that volume, less the number of particles that are removed in that volume. For example, they may become another particle by scattering, or they may not come out at all if they have a photoelectric death. So the equation looks like this in the end. This is the net gain. You can have in scattering, that would be, for example, if you have a high energy photon, it scatters and then becomes an energy photon of interest to you. So this would be energy E is of interest to you. That's the phase space bin. Then a high energy particle could land onto this energy and you would count it. But you also have absorption losses. So if the particles of energy E are removed by absorption, then you got to count that out. Let me do a Mickey Mouse calculation. I love Mickey Mouse calculations because if you can do one, you understand the concept. If you can't do it, you don't understand it. So let's imagine we care about these green photons. They're coming into a voxel. Some of them go right through. Some of them scatter. And also, they liberate an electron. Some of them just liberate an electron but don't scatter. For example, photoelectron. In addition, we have two other energies coming into the voxel. They can scatter and produce green particles, which we are interested in. That's an example here and here. In this case, going back to the green ones, if they lose energy, they don't have energy E1 anymore, so we don't want to count them in our phase space. So let's do the math, and this you can do at your leisure after this lecture, but if you look at these particles with angular direction omega-1 and energy E1, incoming we had 60 of them. Each one of these is 10 photons, 60. Outgoing, we have 50. So we had a loss of 10 in that bin in phase space. And the divergence ends up showing that it's minus 10. And the dose from these green particles is 10, the negative of the divergence, which is some of the equations I showed earlier. So this all tallies up. The bottom message here is that the Monte Carlo method is an auditing bookkeeping method, and it forces agreement by mass energy conservation between these two methods, the rows and columns in your bookkeeping book. The eclipse algorithm is called Accuros, and there are many steps involved. The patient is actually quantized into a, I forget what the name is now, let's see, finite elements like this. And then eventually we obtain, after all this is done, we obtain the electron fluence. Remember, all dose is deposited by electrons. So it calculates the fluence of electrons and you can get the dose out of it. And that's what that looks like. Again, if you know the stopping powers of the materials and you know the fluence of the electrons or positrons, you can get the dose. And the Accuros implementation was largely due to this gentleman, Todd Waring. And The solution, sorry, I have a phone call. I will ignore that. A large system of coupled equations are required, and I think of this as a reconstruction algorithm, solving for fluences consistent with mass energy conservation. Very high demand on computer memory, tens of gigabytes, a series of expansions of some functions, phase space quantization. The quantization is not one EV per bin. It's they're grouped, and similarly the angles are grouped. And finally we have finite elements of the patient, and there are some physics simplification. Pair production, positrons are treated as electrons, and there's no Bremsstrahlung. So there's a bit less physics in this method, but the results are spectacular. 86 seconds for this lung treatment, rapid arc 6 MV, and here we go for another one here, a head and neck case in 163 seconds. These are remarkable achievements. Okay, what's the state of the art? This is here strictly for your review afterwards, comparing Monte Carlo and Boltzmann equations. The important thing is, in a Monte Carlo method, one particle at a time is dealt with. And so it's a very, you might say, sluggish technique, whereas in the Boltzmann equation, we solve for cohorts of particles. These methods are all interrelated. They solve the same problem. They have to be interrelated. The linear Boltzmann equation is really the grandfather of all these methods. If you apply a Green's function technique, which some of you may have learned in electrodynamics, you can end up deriving the convolution algorithm. And so there's a connection here between deterministic doses and this. If you have a Monte Carlo stochastic integration of an integral, you get this, and then you can provide kernels to the convolution method. So they're all interconnected. And now as far as accuracy, we've seen major improvements in accuracy with these techniques. And now we're into this region here where we've gotten the best accuracy that has ever been achieved with these two methods. And remember that this scale of computation time is constantly going to the left, and maybe we can thank the video game industry for creating these super fast computers. Those of you who are computer people, you need about 10 teraflops per second of performance if you want to play in this domain of algorithm. Now, which is better as far as speed, Monte Carlo or Boltzmann? It depends on the complexity of the problem. And at the moment, it looks like they're almost the same for a complexity being an IMRT plan. But if we get into more complicated situations, the Monte Carlo method actually stays pretty flat and won't change much. But the Boltzmann method will get more and more complicated with the complexity of the problem. If the problem is simple, the Monte Carlo method is advantageous also. So, let me go back one. So it is a two-horse race as far as these calculations. This Watch Me Bolt is the name of the horse. He's quick starting out of the gate. That's here. And the other one is called the Monte Carloist is here, slow. And he's a slow starter, but he has endurance because out here, he won't take that much more time. He'll be pretty fast. But the Boltzmann, Watch Me Bolt, bolts out of the gate very fast, but then near the end of the race is slowing down. Here's a summary of contemporary algorithms doing different clinical cases. Again, it's for your reference, and I only want to show that you can get these results within minutes, sometimes even less than a minute. And so these methods are not completely out of the clinical realm. Here's examples of Monte Carlo results and of Acuros results, again, with reasonable times. The elephant in the room is what we don't talk about is AI, artificial intelligence, and there's a lot of publications coming out on this that are seemingly affecting how Monte Carlo calculations will be done and so on using AI techniques. So keep an eye on that. I am not an expert on it, but it's certainly a hot topic. So let me close with saying that dose prediction is necessary but not sufficient. What I mean is we haven't really tackled the non-linearity of the biological response for human conditions. We have a lot of cellular data, we have a lot of mouse data, but we're still working on understanding the biological response in the human. We have uncertainties in imaging and in targeting. So just getting a good dose distribution doesn't mean necessarily it will land in the patient that way. Algorithms have assumptions, and some of them are quiet, tacit, they're hidden, so you can't fool the physics, and software is soft. There are frequent updates, so you have to keep an eye on them. Assumptions fail under different clinical conditions, so you should spot check in real or virtual phantoms, and black swan events require vigilance. These are black swan, it's an expression for a rare event with a major consequence. For example, an earthquake. They're rare. When they happen, they have a major consequence. And there may be some clinical conditions where there would be some black swan events in a particular treatment technique. Monte Carlo and Boltzmann methods are competitive right now, but they're not available on every planning system, and they need quite a bit of understanding. And I hope today that we gave you enough information to start understanding these methods. And finally, there's a dilemma right now, because do you trust the dose measurement or do you trust the algorithm? When you do a Monte Carlo calculation, it's a fairly pure computation that takes a lot of things into account that your ionization chamber or other dosimeter gels or whatever may not be taking into account. So we're in a strange place right now. Do you trust the measurement or do you trust the algorithm? And remember, it takes years to develop trust, and it can be destroyed in seconds. So I want to end by thanking my co-authors on this book, which is now available in paperback. And there's also a code if you want to use it, ADC23, at the publisher's website that gives a significant discount if you're interested in the details of everything I've said. And all of these individuals have helped me over the years to understand these methods. If you have any questions later after you ponder the slides, I'd be happy to answer some of them. This is my email address, and I thank you for listening.
Thanks, doctor, for this precious information.
Sorry,
doctor.
Okay, many thanks for the valuable presentation you've just made, Jerry. And it's the time to relax and have a breathe.
Yes, that's correct. Yeah, I apologize for how long it took.
No, that's fine. Yeah. That's why we are really happy. We are really happy with this. But okay. You did a lot. Anyway, it's question time now. Are you happy to take some or to have a rest?
Yeah, I'm fine. I'm fine.
Okay.
Yes.
All right. Okay. So our audience, would you please be concise and clear when facing your question? Raise up. Okay. Dr. Aladdin, possibly you've got a question.
Yeah, thank you. Thank you, Dr. Jerry, for this interesting lecture. Your numerous and variable research contributions have significantly enriched the field of radiotherapy. Dr. Battista, from your long experience, what the current unsolved problem and research areas are that required further studies? And what are your tips for postgraduate students and trainees in this field? Thank you.
So the areas that require further investigation, I think we almost are saturated with regard to dose algorithms. I think that's reached a maturity level that, if we improve things by another 1 or 2%, it may not be clinically significant. So I think that area is not so much for research, but is for deeper understanding, because as I mentioned, there can be some strange results from some algorithms, and you have to be at least aware of them and understand what's going on. So I think that's an area of study, not so much an area of research. I think I don't understand artificial intelligence enough to make a recommendation, but I would keep an eye on those papers that are coming out and try to see how this may all be applicable to the radiotherapy condition. On a bigger front, I mean, a long time ago, I was involved with an accelerator that produced carbon ions, heavy ions, and that was quite fascinating, but it wasn't terribly practical because of costs and so on. But I think synchrocyclotrons have come down in price, and it would be an area that's pretty fascinating if you have these accelerators in Iraq, and I'm not sure. Japan has been very successful with those accelerators, and they're quite nice because they have physical advantage of Deptos curves, basically, but also biological boosts. Because it's high LET, you can create a bigger explosion in the target than in the normal tissue. So I think those might be worth a second look now that they're more economical. Imaging never stops. I think it's a very rich area. Looking at MRI pulse sequences, there's so many possibilities there. So I think I would not. My tip is don't just learn everything about radiotherapy or imaging. I think you are in a world where you must be an expert in both.
Many thanks. I think we've got one of our colleague posed a question. What is relative accuracy of this method?
Well, I think sorry, I'm getting some ringing here. Let me just pause for a minute, okay? Yeah.
Right.
Okay, so I think I've basically answered the questions later on. The question was posed at 211. Okay, it's recent. So the relative accuracy of these methods. So I think the Monte Carlo and Boltzmann methods are in a very tight race. I think either of them will produce the same result. If you run the Monte Carlo for a long time, it should converge to the Boltzmann one. The Boltzmann has a bit less physics in it. So if you're in a situation where there's a lot of pair production, for example, if you had a prosthetic hip implant and you wanted to look at the interface effects near the hip implant, Boltzmann will not do that. So other than those complicated situations, the two of these methods should yield comparable accuracy. And the convolution method, the superposition method, is still very viable in most situations. So I would not throw that one out. I'm thinking it might be used more for redoing a treatment plan while the patient is on the treatment table, so that you could use convolution superposition if you're doing interactive replanning at the treatment machine. But if you want to verify that, then you would have to use the Monte Carlo or Boltzmann if you have a very odd situation.
Thanks. So is there any question, please, guys? Naba Muhammad Ali. Okay, go ahead.
Hi, doctor. How are you? I'm Naba Muhammad Ali, one of the I'm the secret keeper of the society. It's nice to hear you and to listen to your precious information, actually. Sorry, previously I didn't raise my hand. It's just a mistake. I'd like to ask you about, yes. I'd like to ask you about this algorithm. Can it apply on the Gamma Knife software?
Yeah, could you repeat the question again? Yeah.
Can we apply these algorithms on Gamma Knife software?
So I don't understand the last few words, but if it's a Gamma Knife, there's no reason that these methods would not apply. there's no violation of any of the assumptions as far as I know. Did you mean the cyber knife or the gamma knife with cobalt?
The gamma knife, cobalt.
Yeah, so the
Cobalt.
cobalt is your friend. Cobalt, the problems of disequilibrium are minor because the range of the electrons is only 5 millimeters in water, approximately, Dmax. And if you have major inhomogeneities in lung, that range will expand. But the gamma knife is used in the head, right?
Yes.
So yeah, so I don't foresee any problem with using these techniques in the gamma situation.
Thank you a lot. Thanks.
Okay.
Okay, thank you. Thank you for both. So is there any question, guys? Audience? Do we have any? No hand raised up. Okay, let me ask some question or one question. Is there a relation between the number of histories and the accuracy of the results? You've been through this point really.
Yeah, so with regard, this applies to the Monte Carlo
Yes,
calculations.
yes,
Yeah,
yes.
unfortunately, the accuracy depends on the square root of the number of histories. So if you want to improve dramatically, you have to run a lot more because you only gain by the square root of the number of histories. So there comes a point where you reach the level of accuracy that you want, and you have to turn it off because you're not going to get much more without doubling or tripling or 10 times the number of histories. But yes, it's very predictable. The EGS Monte Carlo code, EGS, can provide you actually with an estimate of the uncertainty as it goes. So it can show you, the dose here is whatever it is, 3 centigrade or whatever, and then it can show you plus or minus a value, and then you can decide in this region that's good enough for me, and you could turn it off, right? But that I'm speaking from an experimental code, not necessarily how they were implemented on the different commercial platforms, because they will do different things. And I would keep an eye on it because sometimes there's computer people who take shortcuts, and they might throw away some physics.
Okay, thank you. So more questions, guys? We've got Dr. Asad Hamid Ismail. Yeah, now you all go ahead. Dr. Asad.
Yes. Very good evening. Thank you so much, Prof. Jerry, for the very interesting topic, radiobiologicals. My questions is about the impacts of megavolt of X-ray comparing with the kilovoltage of X-ray, the impacts of the hematological and biochemical tests of the patients. Have you any information about the side effects of this technique on the hematological of the patients or biochemicals composition of the blood? Because I have read a research paper about the comparison between the results of kilovoltage and megavoltage of X-ray. I found that there's some risks on the mutation also if the times of exposure repeated 2 times per year on mutation of DNA and an addition of its impact on the hematological parameters.
So I don't have much information, unfortunately, but I can tell you some of my experience with kilovoltage X-rays. We had developed a long time ago a kilovoltage X-ray needle that you could insert into the patient, like brachytherapy, and then turn it on. And what we were experiencing is that you can if you added iodinated compounds to the specimens, the cells, right, and they took in the iodine, then when you shine with kilovoltage X-rays, you get the release of Auger electrons, and the radiation damage, DNA damage, is enhanced through the use of these compounds. They're called IUDR, iodinated deoxyuridine. And so X-rays liberate lower energy electrons, and also the X-rays can also cause the liberation of secondary electrons that are quite toxic. So there is a difference. The higher energy electrons from megavoltage, they tend to stream. They tend to go, many centimeters and pass through the DNA. Whereas the kilovoltage ones, if you have iodine doping in the DNA, they can release Auger electrons. So that's from the photoelectric effect that you don't have much of in the megavoltage range. So I don't know about the hematological effects, but if there are, iodinated or similar high atomic number materials in the neighborhood of DNA, then there would be the photoelectric effect and enhancement.
Sorry, you mean the intensity of X-ray does not affect on or what? Just regarded to the contrast material, you mean contrast materials? As iodine?
Yeah, the experiments we did, we wanted to see if the contrast material worked, and so we had cells, and then we had the X-ray needle exposing the cells, and we needed the contrast agent to cause this secondary explosion of Auger electrons. If you don't put a contrast agent in, then you just get the usual radiation effects without this extra boost.
Got it. Thank you very much. You're welcome again.
Oh yeah, thank you. Thank you very much for your comments. Yeah.
Okay, thank you. Thank you, Dr. Asad. Thank you, Dr. Jerry. I think I've got a question just been posted. Okay, is Monte Carlo algorithm the newest, or there is a newer algorithm?
So the newest algorithm is the Eclipse Acuros Boltzmann method. In the history of the algorithms, Acuros is the latest one. Monte Carlo has been around a long time, has got a longer history, but it wasn't practical until recently. So you might find that in a certain planning system that Monte Carlo suddenly appeared. That's just because of the computational speed that it was hidden for a while. But the newest kid on the block is the Boltzmann method. Yeah.
Okay, thank you. Any more question, guys? Or no more question? No more question? So at this point, I'd like to give the word to Dr. Mustafa if he wants to say something. Dr. Mustafa, before I.
Thank you, Prof. Hussein. Thank you, Prof. Jerry. We are very happy with you, and thank you very much for your effort. Thank you so much.
Thank you. Yeah, it was a pleasure, chatting with all of you. So far away from me. I enjoyed preparing the lecture. I expected I might go over time, and I did. But there's a lot of information, and I have provided the slides to Aladdin Al-Asadi, and I've given him permission to distribute them, the PDF files. And I know this is being recorded, and you can also replay this if you find that some areas were not as clear as they could have been. So thank you for your hospitality.
Right. Okay. At the end, it looks like we are reaching to the end of the session. I'd like to thank you very much on the behalf of Iraqi Medical Physics community, Prof. Jerry, our distinguished speaker. Hope we have you again in the future, if you like.
Well, possibly. It'd have to be on a different topic.
Yeah, possibly.
How about
artificial intelligence.
the physics of the guitar?
It's good, fantastic. Artificial intelligence would be so nice if you like.
I know, I don't know enough about it. I'm starting from
Yeah.
scratch.
No, that's fine. That's fine.
Yeah.
Okay, thank you, and good evening. Thank you.
Good
Thank
afternoon.
you very
Good
much.
afternoon.
Thank you
Good
very much.
evening to you. Yeah.
Thank you very much. Thank you very much.
Thank you. Goodbye, everybody.
Thank you. Thank
Pleasure.
Thank you.
Bye now.
Thank you. Thank you, everybody.
Bye-bye. Thank you.
Bye. Thank you.